While the planets get a lot of the attention in school and by space agencies, there are smaller, less known worlds in our solar system that are just as interesting. 4 of them are known as the Galilean moons, Jupiter's 4 largest moons. Considering they are so close together, they are fascinating because they are so different. You have a volcano moon, a moon that has one of the best chances of containing life out of anywhere else that we know of, the biggest moon in the solar system, and an ancient, scarred moon whose surface can be traced back to the solar system's very beginning. I'm Alex McColgan and you're watching Astrum, and in this video we will go through these special worlds one by one and do a deep dive into what makes each one so unique. By the end of this video, I'm sure you'll understand why they will be the subject of 2 missions this decade from both NASA and ESA. We'll start with the innermost moon, Io. Let's get to know the context of Io a little better. Jupiter has 79 moons that we know of so far. There's a few that orbit close to the planet in and around the planet's rings. Beyond that are 4 large moons known as the Galilean moons, named after Galileo who discovered them in 1610. From innermost to outermost, these moons are Io, Europa, Ganymede and Callisto. Beyond them are the irregular moons of Jupiter, all of which are much further out than the previous moons. Io orbits very close to Jupiter, only 350,000 kilometers above Jupiter's cloud tops. This means from Io's surface, Jupiter would appear 39 times bigger in the sky than our moon. Io orbits Jupiter in only 42.5 hours compared to our moon's monthly orbit. At some points in its orbit, the tidal bulge on Io is thought to be up to 100 meters. This effect is similar to what we see on Earth with the ocean's tides being caused by the moon, although on Earth the effect is much more minimal, the tides only usually shifting about 2 meters from high to low. Io is getting 300% more tidal force exerted on it in comparison to our moon on us because of its close proximity to the biggest planet in the solar system, Jupiter, and the other big moons in the system don't allow the moon's orbit to be any less eccentric, meaning Io isn't going to be getting any respite anytime soon. A day on Io is the same as its orbital rotation, which means that Io is tidally locked to Jupiter. Just like we can only see one face of our moon from Earth, only one face of Io can ever be seen from Jupiter. Io is a pretty big moon, although it is the second smallest out of the Galilean moons. It is comparable in size to Earth's moon and shares a similar density, meaning it has a similar amount of gravity. But interestingly, it does have the highest density of any other moon in the solar system, one of its many unique features. Another is that it is composed of mainly silicate rock and iron, similar to the terrestrial planets and our moon. In comparison to most other big moons in the solar system, which are made of water ice and silicates. Io, in fact, has the least amount of water of any known body in the solar system. Its core is likely to be made of iron or iron sulfides, surrounded by a silicate-rich mantle and crust. The core is not thought to be convecting though, as no magnetosphere has been detected around the moon. The mantle is thought to be liquid near the crust, and is at least 50 kilometers thick. This is where all the volcanism originates. Which brings us to perhaps the most interesting part about Io, the hundreds of huge volcanoes all over its surface. Before the 1970s, we didn't know much about Io at all, although telescopes were starting to pick up hints that the moon was devoid of water and that it may have a surface of sulfur. The first mission to see Io in any kind of detail was Pioneer 11, although the quality was still not great. What it did detect, however, is that Io was made of silicate rock and not water ice, and that it has a thin atmosphere. Pioneer 10 was also meant to take some close-up shots of Io, but this was lost due to Jupiter's radiation interfering with the onboard command system. The radiation Pioneer 10 went through was 10,000 times stronger than the maximum radiation around the Earth. The next missions to Jupiter were the Voyager 1 and 2 missions in 1979. Voyager 1 flew by at a distance of only 20,000 kilometers and was able to take some impressive close-ups of Io's surface. What it saw was a remarkable landscape full of vibrant colors and a total absence of impact craters. It found mountains taller than Everest, as well as volcanic pits hundreds of kilometers wide, and what looked to be lava flows. Most notably, however, was the presence of plumes coming from the surface. This proved that Io is volcanically active, and it is still the first and only place this has been visibly seen beyond Earth, not including cryovolcanoes. Voyager 1 also confirmed that the surface of Io is covered in different sulfur frosts. This is what gives Io its many spectacular colors. It found that it is these sulfur compounds that dominate the atmosphere. Voyager 2 also saw Io in July of 1979, but was much further away at 1 million kilometers, although it still saw 7 of the 9 plumes Voyager 1 saw in March, which meant those volcanoes had likely remained active throughout those 4 months. The really interesting images came about with the Galileo spacecraft that arrived at Jupiter in 1995. The spacecraft wasn't especially designed to study Io, but it was able to acquire some of the highest resolution images we now have of its surface. Sadly though, Galileo never worked at full capacity, as it had quite a few mechanical malfunctions, which means we could have had even better images had it been fully operational. What it was able to see though were plumes from many volcanoes, as well as confirming the volcanoes were erupting sulfur and silicate magmas, similar to what we have on Earth, except the magma on Io is also rich in magnesium. The surface of Io is spectacularly colourful. The yellow plains are composed of mainly sulfur. The white areas are mainly fresh sulfur dioxide frosts. Towards the poles, the sulfur is damaged by radiation, which can be seen as the poles appear redder than the rest of the planet. In other places, the colours of red are the deposits left by volcanic plumes that reached hundreds of kilometres above Io. The most obvious deposit is from the volcano Pele. Sadly, an inactive volcano when Galileo was around, but Voyager 1 was able to see a massive plume when it passed by. In this image, this plume is 300 kilometers tall and 1,200 kilometers wide. In other words, roughly the size of Alaska. Interestingly though, the source of lava flows on Earth are typically the depression you would normally see at the top of volcanoes. But these depressions are not found on high peaks on Io. Instead, you have these lava lakes with high walls along the outside. Here is Loki, the largest volcano depression on Io, 200 kilometers in diameter. These lakes are directly connected to the lava reservoir below, but usually have a thin layer of solidified crust on top. On average, Loki produces 25% of the average heat output of Io, but sometimes the crust on the lava lake sinks back into the lake, causing Loki to produce 10 times more heat than normal. This can especially be seen in one of Io's other big volcanoes, Tvashtar. Normally this area looks like this, but here the crust is seen falling into the lava lake. In this image where there is just white, the radiant energy from the lava curtain was so intense that the camera only registered white. In 2007, New Horizons used Jupiter as a gravity assist on its way to Pluto. It also used the opportunity to test its equipment. It focused its lens on Io during its flyby, and what it saw was amazing. Tvashtar, the volcano I just mentioned, was in full eruption, and the plume could be seen hundreds of kilometers above Io's surface. You can also see smaller eruptions around the moon. I must admit this is one of the most impressive things I've ever seen of space. Even though the volcanoes tend to be flat, it also has some extremely tall mountains, the highest one reaching 18 kilometers tall. These mountains tend to be completely by themselves, not as part of a ridge or a range. Although most are not volcanoes, lava lakes are found near them, indicating there are faults in the crust near these mountains. Another of the unique aspects of Io is its interaction with the magnetic field of Jupiter. Jupiter has an extremely large and strong magnetic field, and Io orbits within some of the strongest sections. The unusual thing about this interaction is that when particles from some of Io's thin atmosphere and its eruptions are lost to space, these particles float in orbit around Jupiter in what is known as a neutral cloud. This cloud can extend far beyond and behind the orbit of Io, but also surrounding Jupiter is something known as a plasma torus, a donut of ionized particles that follows the rotation of Jupiter's magnetic field. The plasma torus rotates a lot faster than Io's orbit, at 70 kilometers a second compared to Io's 17 kilometers a second orbital velocity. Io orbits right through the middle of it, with the particles from the torus bombarding the particles in the neutral cloud, exciting them to higher energies. These newly ionized particles feed into the torus, attracted by the magnetic field lines of the magnetosphere. These particles are lost from the neutral cloud into the plasma torus at a rate of about 1 ton of matter per second, which greatly increases the size of Jupiter's magnetic field. In fact, if it was visible, Jupiter's magnetosphere would be about the same size as the Moon in our sky. Io's interaction with Jupiter doesn't end there. Jupiter's magnetic field lines, which Io crosses, couple Io's atmosphere and neutral cloud to Jupiter's polar upper atmosphere by generating an electric current known as the Io flux tube. A flux tube is basically a concentration of magnetic field lines. The Sun has these between sunspots and is very visible on the Sun because of the charged plasma that flows between them. Io's flux tube causes an aurora trail around Jupiter's poles. This point here is the flux tube from Io striking the upper atmosphere of Jupiter. Aurora are also visible on Io, although they are not just limited to the poles. The different colors represent the different particles being ionized. Green is sodium, red is oxygen, and blue from sulfur. Europa, one of the most exciting moons in the entire solar system. It is a beautiful world filled with mysteries. This is the first ever close-up image of Europa, taken by the Pioneer probe back in 1973. Since then, we've had the Voyager and Galileo probes explore the moon, and with each visit, Europa has never failed to surprise us. We are yet to solve a lot of Europa's puzzles, but there are many things that we are starting to piece together. Let's first of all see where Europa fits into the Jovian system. Europa is the second and smallest of the 4 Galilean moons, although it's still the 6th biggest moon in the entire solar system, just behind Earth's moon, with a diameter of about 3,000 kilometers. It takes Europa 3.5 days to orbit Jupiter once. Interestingly, the first 3 Galilean moons, Io, Europa, and Ganymede, are locked in a 4-2-1 orbital resonance due to their gravitational influence with each other. This orbital resonance and the constant gravitational tugging from the other moons keeps the orbit of Europa from ever becoming completely circular. Due to Europa's slight ecliptical orbit, the magnitude of the gravitational force acting on it from Jupiter increases and decreases as it orbits. This creates tides that stretch the moon's surface. These forces are significant as they have a big influence on the moon's appearance and what goes on under the surface. Europa's surface is made predominantly of water ice. As you can tell, it looks very remarkable and distinctive due to these long, continuous fractures and cracks. These are called lineae, which translates to lines in Latin. These lineae are often only about 1 to 2 kilometers wide but can extend for thousands of kilometers across the moon's surface. We aren't sure how or why these linea are formed at present, but the most likely theory is that as the crust pulls apart from tidal flexing, warmer material from beneath fills the gap, in a similar fashion to the ocean ridges on Earth. In this image taken by the Galileo spacecraft, you will notice some dark brown spots. They are very small, only about 10 kilometers across, and they are known as lenticulae. They are also believed to be formed by the upwelling of hot, less dense material to the surface, either by pushing the existing crust up or by breaking through altogether. Should the underground material have broken through, what we can then see are these strange, unusual terrains called chaos terrains. They are really rough patches surrounded by a rather smooth surface. These spots are expected to be soft and may contain significant information about what's under Europa's surface, which we will get to later in the video. Data from Galileo also indicated that Europa's equator may be covered in icy spikes called penitentes. These vertical cracks may be up to 15 meters high and will have formed from direct overhead sunlight on the equator. Interestingly, penitentes are found on Earth too, in dry regions at high altitudes, although nowhere near as large as on Europa. Despite being roughly the age of the solar system, Europa barely has any craters. Europa has less than 50 major craters, whereas the Earth's moon has more than 5,000 craters with a diameter above 25 kilometers. This indicates that Europa's surface is constantly changing and reforming. Models suggest that Europa's surface is only about 30 to 180 million years old, which is very young in geological terms. Additionally, Europa's icy surface is the smoothest surface of any known solid celestial object in the entire solar system. Its icy crust also has an albedo or light reflectivity of 0.64, one of the highest of all the moons. Europa's albedo makes it 5 times brighter than our moon. The surface is bombarded by a constant and intense blast of radiation from Jupiter. The radiation level at the surface of Europa is equivalent to a dose of about 5,400 millisieverts per day. Exposure to radiation at that level would be enough to kill a human in a single day. The reddish-brown color spread across the cracks and fractures of the moon is believed to be due to salt and sulfur compounds mixing with water ice and then modified by Jupiter's radiation. A recent study from JPL suggests that Europa might even glow in the dark. Energetic ions from the radiation penetrates the surface, which would energize the molecules beneath, which would make them release energy as visible light. Unfortunately, we cannot see Europa's dark side from Earth, as we are between it and the Sun always. So we are going to have to wait for future missions to Europa before we can prove this. Radiation received from Jupiter plays a significant role in Europa's atmosphere as well. Europa has a very tenuous atmosphere, composed primarily of oxygen. Unlike on Earth, the oxygen on Europa is formed by radiolysis, or in other words, the process of radiation bombarding the water ice surface, separating the H2O into oxygen and hydrogen. Hydrogen escapes Europa's gravity altogether because it's so light, whereas a lot of the heavier molecular oxygen remains. The hydrogen and oxygen that escape Europa's gravity form a dispersed neutral cloud, which follows the orbit of Europa around Jupiter. In 2012, the Hubble Space Telescope discovered plumes of water vapor erupting from Europa's south pole. This image suggests that the water plumes rise up to 200 kilometers from its surface. In 2018, astronomers found additional evidence of water plume activity on Europa when they looked back at the old Galileo data with a new data analysis technique. A dedicated mission studying these plumes can also help us understand what's inside the moon without having to land on it. Because what may lie underneath that solid ice surface is perhaps the most fascinating thing about Europa. There is likely to be a global ocean between a rocky mantle and the water ice crust. The first clue that this amazing ocean world was hidden under its surface
was provided by the Voyager and Galileo probes in 1979 and the late 1990s respectively. Between these missions, there was a drastic change in the magnetic field of the Moon, which is not possible unless there is some electrically conductive fluid beneath its surface. Europa's crust also indicates the presence of a liquid layer beneath it, as it rotates with an angle of 80 degrees, which is not possible if the crust and rocky mantle were mechanically attached. Instead, it is likely that the icy crust floats on the ocean, and it is believed to make one full rotation around the Moon once every 12,000 years. The fact that this ocean is not attached also explains the multitude of lineae on the surface. Tidal flexing should cause lineae to form at specific points on Europa, not all over. However, because the position of the crust changes over time, and one spot never stays in the same place for long, hence why more and more lineae form. Europa is 780 million kilometers away from the Sun, which is 5 times further away than the Earth. That makes the sunlight about 25 times fainter here. As such, Europa, or any other moon in the Jovian system for that matter, barely receives any heat from the Sun. So unsurprisingly, it's cold enough here that the surface is frozen. In fact, Europa's surface temperature averages about minus 160 degrees Celsius at the equator and minus 220 degrees Celsius at the poles, keeping Europa's icy crust as hard as granite. However, tidal pressures exerted on the Moon as it orbits Jupiter heats Europa's core, so geothermal activity from the core should keep the subsurface ocean in a liquid state. This ocean is believed to be under only 15 to 25 kilometers of solid frozen crust. The ocean itself is probably about 60 to 150 kilometers deep. Interestingly, Europa is only 1/4 the diameter of Earth, although it may contain twice as much water as all of Earth's oceans combined. What's most interesting about Europa's ocean is that scientists believe that it is in contact with Europa's silicate rocky mantle. This makes Europa's ocean a suitable environment for life as we know it to exist. We believe that life requires water, minerals, and energy to form, and Europa seems to have all these requirements. From the evidence we've seen so far, scientists are extremely confident that this ocean not only exists, but that chemical reactions can take place there, and that there is enough tidal energy heating the core that geothermal activity may exist on this ocean's floor. As we have seen on Earth, whole ecosystems can exist in such places, far from the sun's light. So for now, Europa is one of the most likely places we can find life outside of Earth. Now, NASA's Europa Clipper spacecraft is scheduled to launch in 2022 and is likely to reach the Moon by the end of the decade. It is scheduled to perform more than 42 flybys of Europa. ESA is also working on their own spacecraft called JUICE, or Jupiter Icy Moons Explorer, which will explore Jupiter and 3 of its largest moons, Ganymede, Callisto, and Europa. JUICE is also scheduled to launch in 2022 and is also likely to reach the Moon by the end of the decade. These probes are specifically designed to examine Europa's water plumes and atmosphere. NASA is also planning a Europa lander mission, but this mission is going to launch well after the Europa Clipper mission. These missions will help us know more about Europa and hopefully confirm the answer to the most tantalizing question of all: does it and can it sustain life? At the very least, these missions will give us a new perspective of our solar system and help us understand how it works. So there we have it, almost everything you could want to know about the fascinating world of Europa. Ganymede, the third of Jupiter's Galilean moons, the largest moon that we know of, and home to the largest water ocean in the solar system. But there's something else that sets Ganymede apart from anything else we've seen before. This Jovian giant contains an intriguing mystery buried deep beneath its surface. There are 79 different moons of Jupiter, and Ganymede is the third of a group known as the Galilean moons, Ganymede is the largest of these four, with an impressive diameter of 5,268 kilometers. For a point of comparison, this is 0.41 times the size of Earth's diameter, and 1.02 times greater than the previously thought to be largest moon, Titan. It initially appeared bigger because of its thick atmosphere, which stretches hundreds of kilometers into space. Ganymede's volume is even 26% larger than Mercury's, although it doesn't contain as much mass. Ganymede's average density is 1.9 grams per centimeter cubed, compared to Mercury's 5.4. This is because of its composition. Like Europa, Ganymede's surface is a thick crust of water ice, extending 150 kilometers deep, underneath which is believed to lie a vast ocean of liquid water. And when I say vast, it really is. Because while Mercury has very little water and is rich in dense metals, the abundance of water on Ganymede reduces its average density. The ocean of Ganymede is so big that it contains more water than all the oceans and seas on Earth, and it is estimated to be 100 kilometers in depth on average, 10 times deeper than the deepest point in our ocean. All of this water means that Ganymede is only 50% rock, the rest being water and small amounts of metals and other ices. This seems appropriate to me, as the name Ganymede comes from the classical mythology, where Zeus, or as the Romans called him, Jupiter, claimed a young boy called Ganymede and took him to be a cupbearer for the gods. It seems fitting that the moon Ganymede would also carry so much water around for Jupiter. Interestingly, Ganymede has an atmosphere that contains oxygen. Now you might be wondering, with all this water and an oxygen atmosphere, is it possible that life exists on Ganymede? While it's certainly possible, there are some features of Ganymede that make this unlikely. To begin with, the oxygen atmosphere is very thin. It is estimated to be somewhere between 0.2 to 1.2 micropascals, or about 100 billion to 500 billion times less than Earth's atmospheric pressure at sea level. That would be impossible to breathe. And while our own planet Earth has certainly demonstrated that ecosystems can flourish in the depths of oceans without sunlight to sustain it, there could be a big problem that prevents this from happening on Ganymede. This is because the ocean of Ganymede is so deep that water down at its bottom would likely be compressed back into an ice through sheer pressure. Life in the deepest parts of our ocean can survive thanks to minerals being ejected from geothermal vents. With such a thick ice layer between the core and the ocean, it is unlikely that this would occur on Ganymede. Europa, Ganymede's neighbouring moon, is considered a more likely candidate for life because of this. However, if Ganymede's ocean is salty, which there is an increasing amount of evidence for, it could change the interior makeup of Ganymede drastically. Models suggest that with a salty ocean, it could be that there are multiple layers divided by sheets of ice. If this is the case, the most internal layer could indeed be in contact with the rocky core, increasing the chances of life existing there. But underneath Ganymede's ice and water exists something else truly surprising, something that scientists do not have an explanation for. Somehow, Ganymede is producing a magnetic field. The magnetic field of Ganymede was first discovered by scientists in 1996 when the Galileo spacecraft began a series of flybys of the icy moon. The big indicator of a magnetic field is the presence of auroras, and incredibly, auroras were detected in Ganymede's tenuous atmosphere. Not only that, but as Hubble studied Ganymede over an extended period, it became clear that these auroras didn't wobble as much as expected, likely a result of something known as magnetic friction in a salty water ocean under the surface. A magnetic field is significant, as it's the feature on Earth that shelters the planet from solar radiation, enabling all life to flourish. The field around Ganymede does not completely protect it from such radiation. Being tucked within Jupiter's incredibly powerful magnetic field and radiation belt means it's still getting pelted with a lot of radiation. Ganymede's surface still has about 5 to 8 rem, enough to make a human severely ill or dead in just 2 months. But it's still better than its closer orbiting neighbour moons. Scientists are not quite sure why this magnetic field is here at all. Our planet's core is hot and molten. Convection currents within it move electrons, which in turn produces the magnetic field that surrounds us here. However, this shouldn't be happening on Ganymede. Ganymede is smaller than Earth, and given its size and composition, scientists believe that the core should have cooled down enough by now that it should be a solid mass, not liquid. This would prevent electrons moving through convection and would prevent a magnetic field. And none of the other moons of Jupiter have a magnetic field. In fact, Ganymede is the only moon in the entire solar system that has one. So what's going on? Scientists do not know for sure, but the answer might lie in Ganymede's incredible relationship with its planet and neighbouring moons, and a process known as tidal heating. Ganymede orbits around Jupiter roughly once every 7 days in an eccentric orbit. This means that at some points of its orbit, it's closer to Jupiter than at others. When an object comes under a strong gravitational force, it will stretch in the direction of that force, as mass is pulled in the direction of gravity. However, the further an object gets from the source of gravity, the more it will compress back to its original shape. As Ganymede has an eccentric orbit around Jupiter, it is constantly coming under more and then less gravity, and is constantly stretching and contracting. Have you ever pulled and stretched blue tack repeatedly in your hands before pushing it back to a ball shape? Then you might have noticed that after a while it gets surprisingly warm. This is because stretching produces friction as the material rubs up against itself. And on the scale of moons and planets, this friction adds up. A tidal force creating heat through friction is known as tidal heating. On top of that, in a process I find fascinating, Ganymede has formed an orbital resonance with two of its fellow Galilean moons, Io and Europa, in what is called a Laplace resonance. For each time Ganymede orbits Jupiter, Europa will orbit exactly twice, and Io exactly 4 times. This mathematically precise configuration has not happened by coincidence, but is evidence of the moon's gravities pulling on each other and the whole system attempting to conserve the resulting momentum. However, it means that Ganymede is constantly being pulled by its neighbour's gravity and is under a lot of gravitational stress. So perhaps tidal heating is warming up Ganymede enough that its core remains a liquid after all, helping it to continue to produce its magnetic field. Scientists do not know for sure, but it would perhaps explain why the surface of Ganymede is so interesting. You may have noticed that Ganymede's surface is split into large, dark regions that cover about 1/3 of its surface, and lighter regions that make up the other 2/3. Through examining the number of impact craters on these two sections, scientists can tell that the dark regions are actually older than the lighter ones, as they contain more craters. The lighter regions might have fewer craters, but they do contain long ridges and grooves up to 700 meters high and thousands of kilometers long. Truly an impressive sight. But again, scientists are not sure how these ridges formed. One explanation is that tidal forces stretched out the surface of the moon in an unstable period of Ganymede's ancient history. Perhaps this same tidal force could have also warmed Ganymede's core and preserved its magnetic field. Whatever its cause, the magnetosphere of Ganymede has been instrumental in helping scientists understand the composition of the moon. By measuring the areas that auroras appeared in Ganymede's atmosphere, scientists were able to confirm the existence of Ganymede's subsurface oceans, all without having set foot there. And as for the rest of Ganymede's mysteries, maybe JUICE, the Jupiter Icy Moon Explorer, will find us the answers. The ESA spacecraft is set to launch in 2022, and though it won't reach orbit around Ganymede for another 10 years after that, is to investigate the inner workings of a number of Jupiter's moons, including Ganymede. Until then, we may have to let Ganymede's mysteries remain just that, a mystery. Callisto. Despite the fact it is the 3rd largest moon that we know of, I think the majority of people would be hard pressed to say any facts about it at all. Is it just a boring world? Or do we simply not know much about it? Actually, we know more than you may first assume, and it is far from boring. Let's start with where it fits into the Jovian system. Callisto is the 3rd largest moon in the entire solar system, and it's just smaller than Mercury at 4,820 kilometers across. However, while its diameter is only 58 kilometers less than Mercury's, it is only 1/3 of the mass of the planet, meaning it's less dense and its gravity is a lot weaker. It is the second largest of the Galilean moons and orbits Jupiter much further out than the other three, taking 17 Earth days to do so at an average distance of 1.9 million kilometers. Even at this distance, it is still tidally locked with Jupiter, meaning the same side of Callisto always faces its parent planet. However, it does mean that it is not locked in an orbital resonance with the other three moons, nor do we believe that it ever was. Callisto has a very tenuous atmosphere composed of carbon dioxide and possibly oxygen too, although oxygen has never actually been detected yet. We know, however, that the atmosphere is so thin that the molecules contained within it do not collide, and theoretically the atmosphere should be stripped away by atmospheric loss processes in just 4 years. Scientists believe that Callisto's crust is replenishing the lost atmospheric particles through sublimation of carbon dioxide surface ices, evidenced by some interesting surface features. Now, the surface of Callisto is one of the most ancient in the solar system, with evidence placing it at over 4 billion years old. You'll immediately notice the speckled nature of Callisto. Its surface is completely covered with various sized impact craters, more so than any other object we've observed. In fact, it's close to saturation. Any new crater will probably just overlap another one at this point. Without any geological activity, cratering is perhaps the only process that has vastly been impacting Callisto's appearance over its lifetime. Why is Callisto's surface so old compared to a lot of other bodies in the solar system? Well, on geologically active planets like Earth, there are processes that can erase almost all evidence of past impacts. Earth has one of the least cratered surfaces in the solar system because so much happens on its surface. It has weather, water, plants, volcanism, tectonic plates, and human activity. These act together to break apart, wear down, and lift up the ground. Even other Jovian moons like Europa or Io have comparatively fewer craters thanks to tidal forces, which cause geological activity on their surfaces. This doesn't happen with Callisto. Callisto does not show any signs of geological processes such as volcanism or plate tectonics, and so its surface has remained intact after all these years. Limited tidal forces and thus no geological activity impact Callisto in another very unique way. There are no mountains to speak of on its entire surface. When Callisto initially formed at the very beginning of the solar system, it was likely an ocean world that has since frozen over, and apart from the bombardment of meteors, it has stayed exactly the same ever since. So let's have a look at some of these craters, because some of the biggest are truly impressive structures. This is Asgard, the second largest impact crater on Callisto, measuring 1,600 kilometers in diameter. And this is Valhalla, the largest multi-ring impact crater in the entire solar system, with a diameter of 3,800 kilometers. It's these craters that add to the unique appearance of Callisto, as they contain more rings than craters anywhere else. With these craters, the impactor was large enough that it may have completely punctured the thin crust, with it eventually refreezing over in the light patches you see in the middle. Zooming in on these middle regions, you'll notice they have a mottled appearance. There seems to be a big difference in contrast between the bright knobs and the darker plane. These regions are a lot less cratered than the rest of Callisto's surface, which would make sense if the plane truly is a refrozen surface, likely making it 2 billion years younger than the rest of Callisto. The rings are likely fractures in the crust, a concentric failure in the brittle shell of the moon. Interestingly though, within the rings, these bright knobs are still visible. So what are the knobs? Well, they are believed to be the degraded remains of the millions of crater rims from Callisto's past. We don't know exactly why they have degraded so much over time, but perhaps it's due to micrometeor impacts, or simply the ice is slowly sublimating over time. They are brighter than the lower planes because the rocky debris from the meteors and micrometeors will have fallen down the knobs over time, leaving the pure ice exposed at the top. Smaller impact craters are also fascinating due to their uniqueness. Most impact craters are shallower on Callisto compared to our moon. For instance, the Luffen impact structure. It's well over 100 kilometers wide, however, it's only 600 meters deep. This could be because the impactor was breaking apart before it impacted, causing more of a spread out shotgun effect on the surface. Or it could be that the surface has since leveled off from other, larger nearby impacts that have occurred later on. This crater is believed to be over 1 billion years old at least, yet you can still clearly see the ejecta that has streamed away from the impact, clear evidence of how unchanging this remarkable moon is. With some craters, like Rhea crater, there is even a large dome found in the middle. With typical large impacts on other worlds, you will see a few concentric rings and a raised peak in the center. This is very much the case on our moon. However, Callisto has some remarkable examples of large craters where just the opposite happens. Look at Tinder here. Instead of a peak, there is actually a pit in the center. Why does Callisto have such unique craters? It could be due to the fact that Callisto's crust is not just brittle, but pretty thin too, with either soft ice or a salty ocean underneath. Estimates put the crust at 80 to 150 kilometers thick. The Galileo space probe, which spent several years around Jupiter, spent a significant chunk of its time aptly studying the Galilean moons. Galileo found that Jupiter's magnetic field could not penetrate through Callisto, implying there is a highly conductive layer under the surface at least 10 kilometers thick. This couldn't have happened in ice or silicates unless the ice layer is at least partially molten, or very large temperature gradients can be maintained below the ice to create a conductive effect. Data also suggest that Callisto has a small silicate core at its center with a radius of about 600 kilometers. Which begs the question, can Callisto be conducive to life like other icy worlds with water mantles under their surfaces? Well, life as we know it requires liquid water and energy to exist. Callisto might have an ocean of liquid water under its surface, but being about 800 million kilometers away from the Sun, it barely receives any heat from our star. And the absence of tidal forces doesn't help either, leaving radioactive elements the only source of heat to warm this subsurface ocean, if it exists. And unfortunately, even visiting Callisto won't prove anything. Moons like Europa and Enceladus have vents ejecting water directly from their subsurface oceans, meaning we can investigate habitability prospects without ever going into the oceans themselves. No such vents exist on Callisto, so scientists would have to penetrate the crust in order to find out. All these things combined mean that, unfortunately, scientists think that the environmental conditions necessary for life appear to be less favorable on Callisto than on any other icy worlds. Nevertheless, Callisto shouldn't be ignored. If we ever go to explore the outer solar system, Callisto would make a perfect base. You see, orbiting at a distance of 1.9 million kilometers from Jupiter means that Callisto is located beyond Jupiter's main radiation belt, making its environment thousands of times more conducive to human exploration than its inner moons. Callisto also has a lot of water ice that can be used for propellant production, and of course is the staple to keep humans alive. Separating the hydrogen from oxygen also leaves oxygen for breathing. Callisto's geological stability would make for building structures on the surface relatively worry-free, and the lack of huge mountains or deep trenches means it's faster, easier, and more efficient to travel over. From Callisto, we could better explore the inner Jovian system from a safe distance, or use it as a way station for heading farther into the outer solar system. Lifting off from Callisto would be ideal thanks to its low gravity, and you could get a gravity assist from a close flyby of Jupiter. It's true that this is a futuristic prospect, although if we ever do become a spacefaring species, this is a distinct possibility. Now, while Galileo did an admirable job studying Callisto during its few flybys, there is still a lot of information gaps that need to be filled. With any luck, we'll get that from the European Space Agency's Jupiter Icy Moon Explorer, due to launch in 2022, which will reach the Jovian system by 2030 and will explore Jupiter and 3 of its largest moons, Ganymede, Callisto, and Europa. ESA has planned several close flybys of Callisto during this mission. This mission might provide more insight into questions like, does it have a subsurface ocean? And if so, does it or can it sustain life? Beyond that, there's also the questions we haven't thought to ask yet. Who knows what more we will still discover about this incredible moon? So there we have it, almost everything you could want to know about the Galilean moons of Jupiter. In the vast expanse of our solar system, orbiting the ringed giant Saturn, lies a world of ice and mystery. This is Rhea, Saturn's second largest moon. Although you're more likely to have heard of its larger sibling Triton, Rhea is a fascinating place in its own right and harbours many secrets and wonders. Ice cliffs, hundreds of meters high, an internal structure that defies scientific models, and the enigmatic discovery that lingers around this moon that's equally as strange as the thing we didn't find. It's time for this lesser-known moon to step out from its larger sibling shadow. Let's learn all there is to know about Rhea. I'm Alex McColgan, and you're watching Astrum. Join me today on a voyage of discovery to the Saturnian system and the moon Rhea, to see what scientists have discovered there and to witness its beauty for ourselves. Rhea was discovered on the 23rd of December 1672 by Giovanni Domenico Cassini, the Italian astronomer who made numerous contributions to our understanding of Saturn and its moons. Named after the Titan goddess Rhea in Greek mythology, this moon has been a subject of fascination for astronomers and planetary scientists for centuries. Let's start with the basics. Rhea is the second largest moon of Saturn, after the mammoth Triton. With a diameter of 1,528 kilometers, it's roughly half the size of our own moon. If we were to place Rhea next to Earth, it would stretch from London to Warsaw. Rhea orbits Saturn at a distance of about 527,000 kilometers, completing one orbit every 4.5 Earth days. It's locked in a synchronous rotation with Saturn, meaning the same side always faces the planet, a common feature among large moons in our solar system. The surface of Rhea is one of the most reflective in our solar system, with an albedo of 0.7. This means it reflects 70% of the sunlight that hits it, appearing bright white against the backdrop of space. This high reflectivity is due to its composition. Rhea's surface is primarily made of water ice. But this doesn't make it a featureless ice sheet. Far from it. The moon is heavily cratered, telling a story of ancient impacts and a long, violent history. The largest of these craters, named Mamaldi, spans an impressive 480 kilometers in diameter, about the distance from Paris to Amsterdam. These craters aren't just scars on Rhea's surface, they are windows into the moon's past and composition. Observations have shown that the bottoms of some craters appear darker than the surrounding terrain. This could indicate that impacts have excavated material from beneath Rhea's bright surface, possibly exposing darker, amorphous water ice and impact melt. In this photo, you can see a crater in the southern hemisphere of Rhea, surrounded by bright ejecta. But one of the most intriguing features of Rhea is its system of bright, wispy streaks that crisscross its surface. These were first observed in detail by the Voyager space probes in the early 80s, but their true nature wasn't understood until the Cassini mission provided high-resolution images decades later. Initially thought to be deposits of frost or ice, these wisps were revealed to be ice cliffs, some hundreds of meters high. They are likely the result of tectonic activity in Rhea's past, where the icy crust fractured and some sections were thrust upward. These features give us clues about the moon's geological history and the processes that have shaped its surface over billions of years. But Rhea's mysteries don't end at its surface. In 2010, data from the Cassini spacecraft led to a surprising announcement. Rhea appeared to have a tenuous atmosphere or exosphere. A small amount of gas around Rhea is expected, but it was unexpected that there is enough to be measurable. The detected atmosphere consisted primarily of oxygen and carbon dioxide, with the oxygen being about 5 trillion times less dense than Earth's atmosphere at sea level. While incredibly thin, the mere presence of this atmosphere raised intriguing questions about its origin and sustainability. One theory suggests that the oxygen is produced by the decomposition of water ice on Rhea's surface when it's struck by ions from Saturn's magnetosphere. The carbon dioxide, on the other hand, is thought to be the result of organic molecules on the surface being oxidized by the oxygen in the exosphere. This discovery made Rhea the first moon known to have an oxygen atmosphere other than Jupiter's moons Ganymede and Europa. It also opened up new avenues for research into the complex interactions between Saturn's moons and the planet's powerful magnetosphere. Rhea's exterior is fascinating, but what about its interior? Let's dive deeper, literally. While we can't directly observe what's beneath Rhea's icy surface, scientists have used various methods to infer its internal structure. Based on Rhea's average density of 1.236 grams per cubic centimeter, which is only slightly higher than that of water, we can deduce that Rhea is composed primarily of water ice, about 75%, and a smaller fraction of rocks, the remaining 25%. Rhea has often been described as a frozen, dirty snowball due to this structure. This puts Rhea in stark contrast to moons like our own moon, which are primarily rocky bodies. When Cassini visited Rhea, the probe's instruments also provided valuable data about Rhea's composition. Spectroscopic observations confirmed that water ice is the dominant component of Rhea's surface, but they also detected the presence of other materials. One surprising discovery was the detection of carbon dioxide trapped in the surface ice. This finding suggests that Rhea's ice isn't pure water, but contains other compounds, possibly including complex organic molecules. Due to its higher moment of inertia, most scientists believe that Rhea is not differentiated into layers. Instead, it is thought to be a homogeneous mix throughout, with the exception of its core. Some scientists challenged this model though. In 2006, a paper was released in the journal Icarus that suggested that Rhea might have a layer of liquid water under its surface, a subsurface ocean. While this idea is still highly speculative and not as well supported as the subsurface oceans on moons like Europa or Enceladus, it's an intriguing possibility that future missions might investigate. The presence of such an ocean would have significant implications for Rhea's potential habitability and of the conditions necessary for liquid water in the outer solar system. Rhea's interior contains mysteries, but one of the puzzling features of Rhea is its shape. While many large moons and planets tend towards a perfect sphere due to their own gravity, Rhea is noticeably non-spherical. It's slightly flattened at the poles and bulges at the equator, a shape we call a traxial ellipsoid. What's strange is that Rhea's shape doesn't quite match what we'd expect based on its rotation rate. This discrepancy has led scientists to propose that Rhea might have a non-uniform internal structure, with denser material concentrated away from its center. Now, let's talk about one of the most exciting moments in Rhea's recent history, the Cassini mission's close flybys. The Cassini spacecraft, a joint project of NASA, ESA, and the Italian Space Agency, spent over a decade studying the Saturnian system, including several close encounters with Rhea. The closest of these flybys occurred on the 11th of January 2011, with Cassini passing a mere 76 kilometers above Rhea's surface. The last close flyby was on the 9th of March 2013, when Cassini passed just 997 kilometers above Rhea's surface. This close approach allowed the spacecraft to capture incredibly detailed images of Rhea's crater terrain and gather valuable data about the moon's composition, and determined it does not have an internal magnetic field. These flybys provided us with our best look yet at Rhea's surface features. They imaged a landscape dominated by two types of terrain, heavily cratered regions and younger, smoother plains first shown in earlier Voyager missions. The heavily cratered areas we mentioned earlier are thought to be extremely old, possibly dating back to the early days of the solar system. These ancient surfaces provide a record of the intense bombardment that occurred in the solar system's youth. The smoother plains, on the other hand, are likely the result of a resurfacing event, such as from material ejected from large impact events. This material would have fallen back to the surface, filling in older craters and creating smoother regions. But perhaps one of the most intriguing results from the Cassini mission was what it didn't find. Prior to Cassini's arrival, some scientists had proposed that Rhea might have a system of rings. This idea was based on unusual measurements of electron densities around Rhea made by Cassini in 2005. However, despite careful searches during its flyby, Cassini found no evidence of rings around Rhea. This non-detection doesn't completely rule out the possibility of some kind of debris disk around Rhea, but it does make it much less likely. Another intriguing aspect of Rhea is its place in Saturn's complex system of moons. Rhea orbits Saturn in what is known as the E-ring, a diffuse ring of ice particles thought to be supplied by the cryovolcanic eruptions from Enceladus. While Rhea itself doesn't seem to be geologically active like Enceladus, its position in this ring means it's constantly interacting with these ice particles. Although Rhea is in the extremities of the E-ring, beyond where it is dense, over time this interaction could affect Rhea's surface properties and contribute to the moon's bright appearance. As we reflect on what we've learned about Rhea, it's clear that this moon, often overshadowed by its more famous siblings, is a fascinating world in its own right. From its heavily cratered hemisphere to its relatively smooth side, from its tenuous atmosphere to its place in Saturn's complex system of moons, Rhea continues to intrigue scientists and spark our imagination. But our exploration of Rhea is far from over. Many questions remain unanswered. What is the exact nature of its interior structure? How has it evolved over the billions of years since its formation? Could it harbor simple forms of life in a hypothetical subsurface ocean? These questions and more await future missions to the Saturnian system. While there are currently no planned missions specifically targeting Rhea, the moon is likely to be observed by any future spacecraft sent to study Saturn and its moons. As we conclude our journey to Rhea, let's take a moment to appreciate the diversity of worlds in our solar system. From the scorching surface of Venus to the icy plains of Pluto, from the towering volcanoes of Mars to the potential subsurface oceans of icy moons like Enceladus, our cosmic neighbor is filled with wonders waiting to be explored. Rhea, with its icy surface reflecting the distant sunlight, stands as a testament to the beauty and mystery of our universe. As we continue to explore and learn, who knows what secrets this distant moon may yet reveal.
Well everyone, here it is, your most asked for video. Titan. And to be fair, I can understand the curiosity towards it. It is the only moon with a substantial atmosphere. There's clear evidence of stable bodies of surface liquid on it. And best of all, mankind has visited it, so I will be able to show you a lot of real photos and video footage. I'm Alex McColgan and you're watching Astrum, and here is everything you could want to know about Saturn's biggest moon, Titan. But let's start from the beginning and give some context to this remarkable planet-like place. Titan is the sixth spherical moon from Saturn, and unlike Jupiter's 4 Galilean moons, in the Saturn system, Titan is all by itself in its size. The rest of Saturn's moons are pretty small in comparison. To give some idea of how big it is, Titan's diameter is 50% larger than Earth's moon and is 80% more massive. In fact, it's the second largest moon in the entire solar system, after Jupiter's moon Ganymede. It does actually appear slightly bigger than Ganymede if you were to put them directly side by side, but this is caused by Titan's thick atmosphere, which extends its apparent diameter. Even so, Titan's real diameter is still larger than the smallest planet, Mercury, but it's only 40% as massive. As its density is quite low for its volume, its gravity is reasonably weak at only 0.14 Gs, or 1.35 meters per second squared, which is even less than our moon. Due to Titan's low density, it is thought that its composition is half water ice and half rocky material, and like other celestial objects this size, it is believed Titan has a differentiated interior. This means it has layers, and like a lot of other large moons, one of those layers is thought to be a liquid ocean comprised of water and ammonia under the moon's crust. This liquid ocean is comparable to Earth's magma layer, situated between the core and the crust, and has been made liquid due to heat, pressure, and to a certain degree, tidal forces. The existence of this liquid layer was proven more likely when Cassini, the spacecraft orbiting Saturn, discovered extremely low frequency radio waves in Titan's atmosphere. Titan's surface is not known to be a good reflector of low frequency radio waves, but the liquid interior would be. Another reason is that the surface features on the moon have shifted by up to 30 kilometers since Cassini started observations, which could imply that the surface is not attached to the core, but is rather floating on this liquid ocean layer. And while there is no evidence of life on Titan, scientists do speculate that the conditions would be right for there to be life in this subsurface ocean. Unfortunately, if there was life to be found on the surface or below, we'll have to wait a while, as there are no planned missions to check out this possibility, and Jupiter's Europa is a more likely candidate to be investigated for life in the foreseeable future. The differentiated interior of Titan does not produce a magnetic field. Titan is still quite protected from the solar wind though, as 95% of its orbit around Saturn is within Saturn's own magnetosphere. Titan orbits Saturn once every 15 days and 22 hours, and has a rather large orbital eccentricity, which means the orbit isn't so circular. Its orbital plane is also at an angle, but that doesn't mean that Titan is likely a captured object. Rather, like Jupiter's Galilean moons, it is thought that Saturn also had several large moons in the past, but most of these have been destroyed through big collisions, which left Titan the lone victor. Saturn's medium-sized moons, like Iapetus and Rhea, are thought to be the remnants of this tumultuous beginning. Titan's day, like the day on our moon, is identical in length to its orbital period. This means Titan's rotation is tidally locked to Saturn, and only ever shows one face to the planet. Not that visually it makes any difference. Titan's hazy atmosphere completely blocks the view of the surface from an outside perspective. On the other hand, you might just be able to see Saturn while standing on Titan, although the view would be significantly obscured. This does mean, however, that if you were to stand on one spot on Titan, Saturn would never move in the sky. Removing Titan's haze, this is what it would look like. This leads us on to one of the topics that truly sets Titan apart from the rest of the moons in the entire solar system, its substantial atmosphere. I remember the first time I ever saw a photo of Titan, I was truly blown away, as it never occurred to my young self that the moon could even have an atmosphere. I thought it must have been a new planet they'd discovered recently or something. To me, what looks odd about the atmosphere is how far it stretches into space. When you see a picture of Earth, you see that the atmosphere has quite a tight fit around the planet. Titan, on the other hand, looks like it has a thick blanket all over it. There are a number of reasons for this. The first one is that Titan is a lot smaller than Earth, but its atmosphere is 1.9 times more massive than Earth's, or 7.3 times more massive on a per surface area basis. The second reason is that Titan's gravity is a lot weaker than Earth's, meaning it doesn't pull it down as strongly.
the mass of the atmosphere actually means the pressure at the surface is 1.45 atmospheres, or 45% more than the atmospheric surface pressure on Earth. And comparing the two, you can see the extent of how far Titan's atmosphere stretches into space. 600 kilometers high is only the limit of the mesosphere. Earth's mesosphere, on the other hand, stops at 120 kilometers. Even at a distance of 975 kilometers, the Cassini spacecraft had to make adjustments to maintain a stable orbit against atmospheric drag when it made its closest approach. Like Venus, Titan is a super rotator, meaning its atmosphere rotates faster than the rotation of the planet. This can especially be seen at the poles on the moon. Each pole has a polar vortex that rotates once every 9 hours, compared to the moon's rotation of 16 days. The vortexes on each pole seem to be like permanent hurricanes. So what does the atmosphere consist of, and why is it orange in colour? Well, the atmosphere is 98.4% nitrogen, the remainder being mainly methane and small amounts of hydrogen. There are also trace amounts of hydrocarbons from the breakup of methane in the upper atmosphere due to UV light, and it is these hydrocarbons that are thought to give Titan its orange hue. This constant breakup of methane to hydrocarbons should have meant the moon ran out of methane within 50 million years, a very short space of time compared to the age of the solar system. This means there must be a source that replenishes the methane, the most likely candidate being cryovolcanoes, although biological life has not been ruled out. The methane in the atmosphere creates a greenhouse effect, without which the temperature on Titan would be a lot lower. Conversely, however, the haze also reflects a lot of the sunlight, creating an anti-greenhouse effect, which cancels out some of the potential greenhouse effect from the methane. Now, while Titan's upper atmosphere gets 1% of the sunlight Earth does due to the distance from Titan to the Sun, another result of this reflection of sunlight means the surface of Titan only gets about 0.1% in the end. The Huygens team likened the difficulty of taking photos at this light level to taking pictures of an asphalt parking lot at dusk. All these things combined means that while it would be dark, a human would only need an oxygen mask and to wrap up extremely warm to be comfortable while standing on the surface of Titan. It really is cold on Titan, minus 180 degrees centigrade on average. This means any water on Titan remains solid and doesn't ever melt, evaporate, or sublime. Then why are there sometimes clouds on Titan? Well, these are not water ice clouds, but rather methane clouds, which means yes, it can rain methane on Titan. In fact, the temperature on Titan is just right for methane to be liquid. Methane freezes at minus 182.5 degrees centigrade and boils at minus 161.5 degrees centigrade. The temperature, combined with the surface pressure, got scientists very excited at the prospect of there being hydrocarbon lakes or seas on the surface of Titan, similar to water lakes and seas on Earth. If there really were lakes on this moon, it would be the first time this had ever been observed outside of Earth. This was actually one of the main driving forces behind Cassini-Huygens, to see what there was under that thick atmosphere. The Huygens probe, named after the astronomer who discovered Titan in 1655, was designed to enter Titan's atmosphere and land on the surface. The possibility of even landing on an ocean was taken into account during its design process. As the probe descended, its parachute was pulled, and after an almost 3-hour journey, it finally rested on the solid surface of Titan. Sadly, it wasn't able to see any lakes, but what it did see confirmed that methane lakes once existed, as Huygens landed on what appeared to be a dried up lake bed. These stones you see from the surface photos are rounded stones, much like pebbles found in a river or a lake on Earth. Cassini, from the perspective of space, was able to confirm that methane lakes are still found on Titan today. Near the South Pole, Cassini observed an area which was later confirmed to be a lake called Ontario Lacus. It is 20% smaller than its North American namesake, Lake Ontario. So in other words, it is still pretty big at 15,000 square kilometers. On this side of the lake, you can see a smooth shoreline eroded by waves. On the west side, you can see the first evidence of a river and delta on Titan, meaning that liquid hydrocarbons flow down higher planes to the lake, leaving delta deposits in much the same process you would find on Earth. Ontario Lacus is extremely shallow, only estimated to be between 40 centimeters and 3 meters deep. The deepest point likely to be just over 7 meters. As Cassini's radar mapped this lake, it found that the lake did not have waves bigger than 3 millimeters, meaning the surface would appear like a sheet of glass or a mirror. This doesn't mean there can't be bigger waves, unless this liquid is particularly viscous, but the likelihood is that it was simply not a windy day as the observations were taken. The atmospheric density and gravity on Titan should mean that waves would be bigger on Titan than they would be on Earth. As the north pole of the moon began to come out of a 15-year winter, another lake was discovered, Jingpo Lacus. As Cassini was passing by the moon, sunlight was reflected off the surface of Jingpo Lacus like a mirror, directly into the view of Cassini. Upon further observation, Cassini was able to detect further evidence of moving liquid on Titan, as can be seen by these rivers flowing into the lake. The second biggest lake on Titan to be discovered is Ligeia Mare. Found in the north polar region of Titan, it is bigger than Lake Superior on Earth, with a surface area of 126,000 square kilometers. While parts of this lake are reasonably shallow, the average depth is a lot deeper than Ontario Lacus at 50 meters, and some parts of it could reach depths of over 200 meters. Plenty of rivers can be seen flowing into the lake, and there are large islands found around this area here. A particularly curious observation Cassini made, dubbed the Magic Island, is the appearance and disappearance of what appears to be an island. Although scientists are unsure exactly what happened here, the theories are that it could be silt suspended in the lake, bubbles, or subsurface ice rising to the surface as the lake warmed during the moon's spring. But still very curious. The largest lake on Titan, at 400,000 square kilometers, is the Kraken Mare. As you can see, the lake is split up into two main parts, separated by a small stretch quite similar to Earth's Strait of Gibraltar. Its nickname is the Throat of the Kraken. Because of tidal forces and the size of the lake, it's thought the tide changes by about 1 meter, and so this strait may have strong currents and even whirlpools. The Kraken Mare is also quite deep in comparison to Ontario Lacus, but isn't any deeper than 170 meters. So, we know about the lakes on Titan now, but what other interesting surface features might it have? Well, plenty actually. Titan's surface is quite young as 100 million years old, which means its surface must be geologically active. Some scientists believe the dirty ice crust is substantially rigid, although there is some evidence to suggest that there is tectonic activity on the moon, possibly caused by tidal forces with Saturn. The main factor of a renewed surface, however, is likely to be the same thing that produces methane in the atmosphere: cryovolcanoes. Now this is pretty interesting. You know how magma on Earth is pretty hot, but when it comes out of the ground it freezes. Well, Titan has the same thing, except its magma is water and ammonia, and when it comes out of the cryovolcanoes and spills over the land, it too freezes to renew the surface. Because a water and ammonia blend is a lot less viscous than lava, it flows further than lava on Earth. This means mountains are more flat and will never reach the heights of volcanoes on Earth. While it is hard to confirm specific cryovolcanoes on Titan due to the obstruction caused by the atmosphere, the most likely candidate is Sotra Patera, found on the southern hemisphere. In this image, height has been exaggerated by a factor of 10, but it gives a good idea of the size of the dome and the 1.7 kilometer deep pit, the largest that we know of on Titan. The force necessary for this to erupt would have had to have been incredible, and while it doesn't appear to be active now, it is being actively monitored. The fact that lava on Titan is a mix of water and other minerals means the surface could be compared to dirty ice. Because we know the Huygens bounced and wobbled in a certain way as it landed on Titan, we have a rough idea of what the consistency of the surface could be like. Scientists have referred to it as a soft, damp sand. Another theory is that it's like snow with a thin crust on top. Imagine walking on frozen snow. If you're careful, you can walk on a solid surface, but if you stomp too hard, you will sink in quite deeply. And Titan's believed to be something like this. Titan's highest mountains come in the form of ridge belts, like the Rockies in America. These ridge belts could also be a form of cryovolcanoes. The largest mountain on Titan can be found in one of these mountain ranges, known as Mithrim Mons, and it's 3,337 meters high. Interestingly, mountains this tall are thought to be topped with methane snow. Also found on Titan are many gorges, valleys and dunes. Using infrared cameras to see the surface from space, what can also be seen quite prominently are these large patches of dark terrain. Originally, these dark patches were thought to be seas until the Huygens probe landed on one of those areas, known as Shangri-La. They could well have been seas in the past, but now they are plains of dark mineral deposits, similar to the Namib Desert on Earth, where they appear as windswept dunes in some places. Overall, Titan can be compared to Earth in lots of ways. Scientists think that Titan shows signs of what early Earth could have been like, only much colder. It's fair to say that Titan is remarkably interesting, and I can only hope it gets its own mission one day. Cassini has done a great job, but it was never a Titan orbiter, and its mission will soon be over anyway. What I would find extremely fascinating is to explore more of its surface, and hopefully it won't be long until a mission to do that will be approved. Until then, here was everything you could want to know about Titan.
It's been 3 years since Cassini ended its mission by diving into the atmosphere of Saturn. Its mission was tremendously successful, and it was, in my opinion, one of the greatest missions of all time. The data it collected over the 13 years in orbit around Saturn is still being poured over today, as there are still a lot of unsolved mysteries about Saturn and its moons. One of the most impressive discoveries of Cassini was confirming the existence of liquid methane lakes on the solar system's most unusual moon, Titan. But knowing they are there didn't help answer how they came into being. But now, scientists may have come up with an answer. I'm Alex McColgan and you're watching Astrum, and today we will explore everything we know about Titan's lakes, what Cassini has seen and discovered, and how we now think they came into being. There are only 2 places in the solar system that have stable bodies of liquid on their surfaces, Earth and Titan. That doesn't mean they are very similar places though. Earth is a rocky planet with an iron core and silicate mantle. Titan is an icy world. Its crust and mantle are made up of mainly water ice, with a subsurface ocean of water surrounding a rocky core. This means Earth is much denser, and, coupled with its bigger size, means the gravity on Earth is a lot stronger than on Titan. Both worlds have dense atmospheres, but due to their differences in gravity, Earth's atmosphere hugs the planet tightly, while Titan's, although a little more massive in total than Earth's, stretches hundreds of kilometers above the moon's surface. Their compositions are also different. Earth is much closer to the sun, meaning it is much warmer than Titan, which allows there to be an active water cycle. Water is frozen on Titan. However, the temperature is just right for liquid methane to be present on its surface. That means, yes, Titan experiences a methane cycle in a similar fashion to Earth's water cycle. Methane clouds have been spotted in Titan's atmosphere, and these clouds rain liquid methane onto Titan's frigid surface. This process carves out rivers through the surface ices that flow into small seas or lakes. Radar data from Cassini, visualized in these images, clearly show various riverbeds and valleys cut away by the flowing methane. The most prominent of these flow channels are found around Titan's second largest lake, Ligeia Mare. These channels, dubbed Vid Flumina,
are special because they look to be much older than any other flow channel on the moon. The canyons have walls hundreds of meters tall with very steep slopes. Liquid methane is visible in the canyon, but right now it isn't flowing. Rather, it is likely to be a drowned river valley due to the level of Ligeia Mare, although some higher altitude tributaries are likely to still be flowing down into the canyon. The lakes on Titan can be huge. The biggest one, the Kraken Mare, is bigger than the Caspian Sea on Earth at roughly 400,000 square kilometers. The radar data suggests that a lot of these lakes are very shallow, some of them only a few meters deep. Some of the larger ones, however, can have depths of over 200 meters. All in all, this puts the total amount of potential fossil fuels on Titan to over 300 times the proven amount on Earth. The lakes of Titan are surprisingly still. Some lakes do not have ripples larger than about 1 millimeter, meaning it would appear like a glass or a mirror. This came as a surprise to scientists, who expected waves of up to 1 meter in height due to the low gravity and dense atmosphere blowing over the surface. This could mean that there just so happened to not be any wind as Cassini passed over, the lakes are a lot more viscous than expected, or that they occasionally freeze over. One other theory has been proposed, and that is that dense aerosols may sit on the lake's surface, creating a film which prevents waves from forming. The detection of lakes on Titan couldn't be possible without the aid of Cassini's radar instrument and infrared camera to see through Titan's thick haze. These instruments use a process called specular reflection to make observations. The radar instrument detected large dark patches across the surface, which were later confirmed to be lakes by the infrared camera, when sunlight reflected off the lake and into Cassini's view. A bit like what you sometimes see of Earth from space. Specular reflection with the infrared camera and the sun ended up being used a lot to confirm what the radar secular reflection was seeing. Interestingly, clouds and the subsequent effects of their rain were also detected. In the left image you see a light patch indicating dry ground, but a year later the area was imaged again, and this time darker patches can be seen, indicating a very flat surface, highly likely to be shallow and small lakes. The lakes aren't distributed evenly across the moon, rather most of them are found near the poles. However, the Huygens probe, which was part of the Cassini mission and landed on Titan's surface near the equator, did see flow channels around the equator too. But where are the lakes these channels would flow into? Well, this is thought to be the result of seasonal variations, like summer and winter producing different types of weather on Earth. At certain points in Titan's year, rain would fall in these parts and pool on the surface. However, these probably evaporate during the rest of the year, and the rain migrates to the north and south, which is what Cassini and Huygens would have observed. Even though Cassini was in orbit around Saturn for 13 years, that's not even 1/2 of a Saturnian year. Saturn takes a full 30 Earth years to orbit the Sun once, so Cassini didn't capture a complete picture of all the seasonal variations. The lakes likely vary in depth throughout the year, with some potentially drying up completely. There is one other mystery that was thrown up by the Cassini data to do with Titan's lake that may have recently been solved. Some of Titan's smaller lakes have very steep rims that tower above the lake level. This is unusual, as lakes on Earth typically form from erosion processes and dissolving limestone, meaning the rims are shallow and smooth. These are called karstic lakes. But this process doesn't add up for a number of Titan's lakes. Scientists now believe that these could be explosion craters that have since filled up with liquid methane. Models suggest that Titan was once colder, with nitrogen rain and snow instead of methane. This liquid nitrogen would have seeped into the crust, creating pockets of liquid nitrogen. As the greenhouse gas methane was pumped into the atmosphere by cryovolcanoes in Titan's past, the world warmed and would have caused the liquid nitrogen now trapped under the surface to evaporate and expand, building the pressure in the pocket until the lid basically blew off, leaving an explosion crater. There is still a lot to be learned from the Cassini data. The lakes of Titan were just a small aspect of the mission, and scientists are going to be piecing these puzzles together for years to come, better understanding the Saturn system as a whole. I really hope future space agencies will be as ambitious and as successful as the Cassini mission. There is still an awful lot to discover out there. Enceladus. Perhaps one of the most intriguing objects in the entire solar system. And yet it is only the 6th largest moon of Saturn, and in natural light, it looks very unassuming. However, there's a lot more to Enceladus than meets the eye. It's an active, icy world with jets of water vapor pouring out from its southern hemisphere. Thanks to the remarkable Cassini mission, we have studied and observed Enceladus in exquisite detail, and perhaps know more about it than some of the closer and bigger Jovian moons. However, although we've seen a lot from the outside, it's the inside of the moon that still holds so many mysteries. I'm Alex McColgan and you're watching Astrum, and together we will explore some of the most fascinating details of Enceladus, piecing together photos and data from a variety of missions to find out almost everything you could want to know about this special moon. So stick with me on this journey of discovery. Let's first of all discuss where Enceladus fits into our solar system. Enceladus is currently Saturn's 14th closest moon. I say currently, as Saturn has some tiny moonlets hidden in its rings that may or may not be classified as moons in the future. It is the 2nd closest major moon though, second only to Mimas. That means that its orbit takes it just outside of Saturn's major rings. Its orbit follows the planes of the rings very precisely, and it only takes 33 hours to orbit Saturn once. Interestingly, it is in a 2-1 orbital resonance with Dione, Saturn's 4th closest major moon. In other words, it orbits twice around Saturn in the time Dione orbits once. This orbital resonance is believed to prevent Enceladus's orbit from ever becoming perfectly circular, which causes Enceladus to undergo tidal deformation. This is significant, as these tidal forces heat up Enceladus's core. You see, as far as we can tell, Enceladus's surface is predominantly made of clean water, certainly with little to no rocks or much else there. Because Saturn is situated so far away from the Sun, it means the outer layer of water on Enceladus has frozen over. Enceladus is essentially a frozen ocean world, a giant ball of water ice. Because it is free from other materials on the surface, the moon is one of the whitest objects in the solar system, with a bond albedo of 0.81, which is pretty much as high as snow. As such, it is one of the coldest satellites of Saturn, with a noon temperature of -200 degrees Celsius, as the white color of its surface reflects a large percentage of the sunlight reaching it back into space. However, about 30 to 40 kilometers down under the surface of Enceladus, pressures start building, and heat energy generated from the tidal deformation of its orbit has increased the temperature of the water ice to the point where the water at this depth can exist in a liquid form. It could well be that there is an entire mantle or a global ocean of water that the ice crust is resting upon, very much like the magma mantle that our rocky crust on Earth rests upon. At the very least, scientists expect there to be a huge pocket of water under the moon's south pole. How do we know this? Well, the most obvious indication are the huge plumes of water being ejected from the cracks in the crust, something referred to as water or cryovolcanism. These jets are really active, consistently blasting around 250 kilograms of water into space every second at speeds exceeding 2,000 kilometers per hour. This is powerful enough that most of the water vapor particles escape Enceladus's weak gravity, and they end up in orbit around Saturn, forming Saturn's E-ring. This ring around Saturn is very diffuse, and so isn't really visible unless it is backlit by the sun. From this angle, the light shining through the water particles make the ring appear exceptionally blue. In fact, this ring is considered the bluest object in the solar system, even more so than Neptune due to the ring's uniformity. The E-ring is Saturn's second outermost ring, and it is 2,000 kilometers wide. Its shape is also heavily influenced by the orbit of Enceladus. Enceladus's plumes create tendril shapes in the rings as more material erupts out of it. However, these sections of the ring tend to smooth off as Enceladus moves further away along its orbit. During the course of Cassini's mission, Cassini was able to pass through these plumes to detect the substances being ejected from them. Cassini wasn't designed with this in mind. Scientists didn't know about the plumes until Cassini got there. However, Cassini was equipped with an instrument called the Cosmic Dust Analyzer, designed to detect what the tiny dust grains in orbit around Saturn are made of, and it was able to use it for Enceladus's plumes too. As it wasn't specifically designed with this in mind, it might not have given us the full picture of what's in these particles, but while water was the predominant substance detected, amino acids, carbon dioxide, nitrogen, and methane were also found. Amino acids are significant as they are the building blocks of life and can be found around the thermal vents at the bottom of Earth's oceans. Does this mean Enceladus has thermal vents of its own? And if so, do they have ecosystems of life around them? While evidence for an underground ocean is abundant, scientists still aren't completely sure about Enceladus's internal structure. At some points in the past, scientists believed that Enceladus was water all the way through. However, data from Cassini suggests that Enceladus's mass is in fact greater than previously thought, meaning it must have some amounts of iron or silicate material in its core. Scientists are starting to lean towards the theory that the internal structure is differentiated, meaning it's a celestial body with defined layers within it. An object of this size really doesn't have to be differentiated. In fact, it's so small at only about 500 kilometers across that it is right on the borderline of being in hydrostatic equilibrium, or in other words, being rounded by its own gravity. There are a number of objects out there of similar or smaller sizes that are not in hydrostatic equilibrium, like Neptune's Proteus. In any case, assuming it does have a differentiated interior, this core is likely to be predominantly rocky. This is important, as thermal vents in Enceladus's water ocean would have to come from a rocky core. A rocky ocean floor would also provide nutrients and minerals essential for what we believe life would need to form and evolve. Thermal activity clearly does exist due to the way Enceladus has plumes in the first place, and the amino acids detected in the plumes suggest a rocky core. As Cassini passed over Enceladus, it also mapped out the thermal emissions from the moon. It turned out that the jets line up with what has come to be known as Enceladus's tiger stripes. These are large depressions, roughly 130 kilometers long, 2 kilometers wide, and 500 meters deep. It is believed that these are tectonic fractures in the moon's icy crust. What is really interesting about the surface features of Enceladus is that there are virtually no impact craters at all over the southern hemisphere, and not many anywhere else. This implies that Enceladus's surface is very young, as while it does have a thin atmosphere made up from the ejected water from the plumes, this isn't nearly enough to burn up asteroids before they hit the surface. Some water from the plumes obviously settles again on the surface, which smooths it off over time. This is another reason why Enceladus is so round for such a small celestial body. In fact, apart from the tectonic fractures and few craters, Enceladus's topographical variation is really quite minimal. There are no mountain ranges to speak of, although there is what you might call a rough terrain around the South Pole if you zoom in far enough. This is perhaps the highest resolution image we have of its surface, and as you can see, it really does appear like a giant glacier. It's interesting to note that even in this small view, there are some smooth sections of ice, but also jagged regions. Over the North Pole, the clear difference is the number of craters present there. While there are tectonic fractures here too, there are no plumes on this side of the moon, so the surface here is clearly a lot older than around the South Pole, which is why it has more of a cratered surface. As Cassini flew through the plumes around the South Pole, It also took the opportunity to image the surface closely around the tiger stripes. The surface here is pretty incredible, unlike anything you would have seen on Earth. It's like the surface has been folded, squashed, and shifted around, leaving these remarkable fracture lines and formations in the surface ice. The fact that Cassini was able to get so close to Enceladus is a feat in and of itself. It's fantastic that we can have such a close-up view of something so far away. Unfortunately though, since the Cassini mission has ended, we no longer have anything in orbit around Saturn that can study Enceladus further. There have been plenty of mission proposals in the past, but all of them were cancelled before they came to fruition. What would be incredible is a probe that could either make its way into Enceladus's ocean somehow, or at the very least, search the plumes for signs of life. There is already a mission called Dragonfly going to the nearby moon of Titan, however this won't have anything to do with Enceladus. So, although a couple of mission proposals are currently under review to go there, that means we are unfortunately still a couple of decades away at least, which is a shame because who knows what secrets lie in wait under that crust. So, there we have it. A look at the intriguing little moon of Enceladus. The scene is set. Your arch-rival has got you pinned, gun pointed at you with your back overlooking the drop of the tallest cliff face in the solar system, Verona Rupes. This 20-kilometer drop is roughly 16 times bigger than the tallest cliff face on Earth, Mount Thor in Canada, coming in at a mere 1,250 meters. The only advantage you have right now is that you are standing on Miranda, a tiny 470-kilometer wide moon of Uranus, meaning the gravity here is weak. Do you jump and take your chances with the drop? Or have you got more chance with the gunman? Well, let's have a look at a few factors. Miranda is the smallest of the 5 circular moons of Uranus. Being only 470 kilometers across, puts it right on the edge of being in a hydrostatic equilibrium, or in other words, it's just about big enough to be spherical under its own gravity. It's also not very dense, thought to consist of at least 60% water ices. Its small size and low density means its gravity is very weak. Just for a comparison, on Earth, gravity accelerates you towards its surface at 9.8 meters per second squared. On our moon, that's reduced to 1.6 meters per second squared. On Miranda, it's just 0.08 meters per second squared. That means, should you jump, you would have a very gradual descent towards the bottom. But there's another factor. While falling on Earth, after a certain distance you would reach terminal velocity. Air resistance combats the acceleration of gravity, which means your speed would eventually cap out. In a lying position, this is roughly 200 kilometers an hour. Without Earth's atmosphere, jumping out of a plane would mean you hit the ground extremely fast, as there is nothing to slow you down, and Earth's gravity is pretty strong. Miranda has no atmosphere. Again, this means there would be no air resistance to slow your fall. So although you're falling very slowly at first, your speed would begin to pick up, with nothing but the base of the cliff to eventually slow you down. As I mentioned, Verona Rupes is a massive 20 kilometers tall. Such a tall cliff can exist on Miranda because its gravity isn't strong enough to pull it down. We don't really know how it formed like this, as Miranda should be too small for plate tectonics. One theory is that water under the ice crust froze and expanded, forcing the surface to split, creating canyons hundreds of kilometers long. So, a 20-kilometer drop with an acceleration of 0.08 meters per second squared. Well, you may not be surprised to find out that it will take you a long time to reach the bottom of the cliff, 12 whole minutes. That means it won't be The Fugitive scenario, where Harrison Ford quickly jumps off the dam before Tommy Lee Jones can do anything about it. Your arch-rival will have to be quite slow to allow you to jump off before he can shoot you. And should that all go well, by the time you reach the base,
With no atmosphere to slow you down, you will be traveling at 200 kilometers an hour. A parachute won't help you here, but a really big airbag or little rockets might do the job. So there you have it. What would happen if you fell from the tallest cliff in the solar system?
Triton is an exceptionally unusual, although often forgotten moon. It has so many unique characteristics, it makes it one of the most interesting objects in the solar system. But because it is the largest moon of Neptune, the planet furthest away from us, it also means that we have only visited it once. Very briefly, as Voyager 2 flew by all the way back in 1989, 30 years ago. But what did the visit reveal, and what have we found out about it since? I'm Alex McColgan, and you're watching Astrum, and together we will find out everything there is to know about the fascinating world of Triton. First of all, let's discuss where Triton fits into our solar system and its local system. Triton is one of 14 known moons of Neptune. 7 of these moons are regular moons, or in other words, moons that orbit along Neptune's ecliptic with very circular orbits, or orbits with very low eccentricity. After these inner regular moons, we get to the irregular moons, the first of which is Triton. An irregular moon is a moon that follows an inclined, eccentric, and often retrograde orbit. This by itself is already where Triton is set apart from any other spherical moon in the solar system. It has an irregular orbit. Triton orbits clockwise around Neptune, as Neptune rotates counterclockwise. And Triton orbits at a 130-degree angle to the ecliptic of the planet. Although, it should be noted that its orbital eccentricity is close to zero, its orbit is almost perfectly circular. All other large moons in the solar system are regular moons, orbiting the same direction as the rotation of their parent planet. What this heavily implies is that Triton did not form alongside Neptune, but it is in fact a captured object. Specifically, a captured dwarf planet. No wonder then that it is by far the biggest of Neptune's 14 moons, comprising 99.5% of the mass found in Neptune's orbit. But how big is that in scales we can relate to? Well, it is the second largest moon in relation to its parent planet, second only to Earth and its moon. While it is smaller than our moon, it orbits closer to Neptune than our moon orbits Earth, which means it appears about the same size in the sky. It is the 7th largest moon in the entire solar system, and most interestingly, it is bigger than Pluto. Pluto is often considered the king of the Kuiper Belt, the biggest object that we know of that formed there, until we consider that Triton once ruled that area before Neptune captured it. So, although Triton is a moon of Neptune, it could be said that it is the biggest and most massive Kuiper Belt object. Further evidence for this was found as New Horizons passed Pluto in 2015, suggesting Triton and Pluto share a near identical composition, which supports the theory that they share a common origin. Beyond Triton are 6 other irregular moons, found much further out. They are almost certainly captured objects too, with unusually eccentric orbits that take years to complete. They were probably perturbed into these weird orbits by the gravity of Triton. So, if Triton was a captured object, how did that happen? Objects need to lose momentum to be captured, otherwise they would have enough momentum to escape. Well, we can't know for sure, but the leading theory right now is that Triton was once part of a binary system, perhaps like Pluto and Charon. As Neptune approached Triton and its moon, the gravity from the encounter would have caused the binary system to fall apart, with Triton's moon being slingshot away and Triton losing enough momentum to be captured in orbit around Neptune. I mentioned that Triton shares similar characteristics with Pluto. What exactly does that entail? Well, they both have a predominantly nitrogen ice surface with other ices mixed in, like water and carbon dioxide. It has quite a flat terrain. Its topography never varies by more than a kilometer. Although Voyager 2 did see ridges and troughs, plateaus, and ice plains. What you may find unusual though, is that it has very little in the way of craters. This implies its surface is very young and is constantly being renewed. Like Pluto, it also has some reddish patches, which is thought to be methane having reacted to UV light from the sun, producing what is known as tholins, an organic compound that has a supposedly tar-like consistency. While organic compounds do not mean life is present there, organic compounds are the basic chemicals from which life forms. Life likely couldn't exist on the surface of Triton anyway, as it's far too cold and the sun far too dim to support any life form that we can imagine. But what's interesting is what could be found under Triton's crust. Under Triton's surface is thought to be a rocky and metallic interior, which gives Triton a reasonably high density for a moon at 2 grams per centimeter cubed. Because of this, and also due to the big step up in size from the next biggest moon in the solar system, Titania, it has more mass than all the moons smaller than it in the whole solar system combined. The radioactive decay from the rocky core could be enough to heat and power convection in a subsurface ocean of water, much like what is thought to be under the surfaces of Europa, Enceladus, and some other large moons in the solar system. And just like Europa and Enceladus, cryovolcanism is an active process today on Triton. Liquid water in the mantle erupts onto the surface like lava on Earth. This is the main reason why the surface is so young. It is being actively renewed by liquid water erupting and then freezing on Triton's surface. Some very young lava plains have been identified, sparse and flat regions, yet, interestingly, with a wall that surrounds the plain. This is called a planitia, or in other words, a solidified lava lake. We also can see caldera, which is the collapse found at the center of a cryovolcano, where lava plains formed from. It is thought that the water from these eruptions would have also brought minerals from the underground oceans onto the surface, perhaps even being the source of the tholins and organic matter I mentioned earlier. If this is the case, and organic compounds are found in the subsurface ocean, it means that there's a possibility that conditions are right for life to have been able to form there. We also see long lines permeating over the surface. These are likely faults, caused either by tectonic activity or freeze-thaw weathering processes. If we look at some more of the Voyager 2 images of Triton, we can see the results of some recent eruptions. You'll notice what looks to be dark deposits on the surface, in cone or funnel-like shapes, up to 150 kilometers long. However, these smaller eruptions may not originate from the mantle itself. Voyager 2 spotted some plumes reaching 8 kilometers high, but these are thought to be because of a solid greenhouse effect within the moon's icy crust. Imagine the surface of Triton, consisting of a clear ice, which has settled on dark deposits like tholins. The sun shines through the ice, warming the darker, more absorbent tholins beneath, which sublimes a pocket of ice under the surface. As the ice is sublime, the pressure builds in the air pocket until the surface above the pocket gives way, causing an eruption. This eruption also takes the dark deposits with it, spreading them out over the surface again. If this is the case, a very similar process has been seen on Mars's poles, with carbon dioxide ices and darker deposits under the ice layer. This process can only exist because of one thing: Triton has an atmosphere, although not as thick as scientists were initially expecting. Triton's atmosphere is thin, only 0.014 millibars, about the equivalent of 80 kilometers up on Earth, although, like Pluto, this density varies through seasonal changes. Since Voyager 2's observations, Triton's atmosphere has become denser as the surface has warmed, evaporating a little of the nitrogen ices on the surface. However, when Voyager 2 passed, Triton's atmosphere was still dense enough to support weather up to 8 kilometers above its surface. In this image, you can actually see clouds on Triton. And going back to the image of the plumes, you can see the deposits from the eruptions all end up facing the same direction, due to a prevailing wind in that region of the moon. Like Pluto, Triton's atmosphere is hazy, the cause of which is thought to be hydrocarbons in the atmosphere not yet broken down into tholins by UV light from the sun. The constant depositing of organic compounds through cryovolcanism, ices evaporating and freezing again through seasonal variations, and a weather-rich, active atmosphere makes Triton a very dynamic world, unlike most other moons in the solar system. It is more a dwarf planet than a moon, likely a sibling of the more famous Pluto in the Kuiper belt. All of these factors combined make it one exceptionally unusual moon. And there we have it, everything you could want to know about Triton. Thanks for watching. I really want to give a huge thank you to our astronauts on Patreon. It's really becoming a thriving community, and I've loved reading all your messages and comments over there. If you'd like to join in, then you can visit the link in the description to become an astronaut and bring the channel more stability than the algorithm. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.